Large language models may seem to have arrived all at once. They did not. This video walks an early part of that story, from 2013 to 2018, 5 advances, each one removing a concrete limitation of the one before it. No background in language modeling is assumed. General quantitative comfort is enough. One question runs through the whole sequence, asked in progressively more powerful ways. How should a machine represent and manipulate language? Each answer made the next one reachable. Here is the road ahead. Words become geometry. Whole sentences get mapped end to end. Attention relieves a bottleneck. The transformer rebuilds everything out of attention alone. And pre-training turns one model into a foundation for many tasks. By the end, you should be familiar with this story yourself, naming each step, dating it, and saying what it unlocked. 2013. The initial step in the journey was to give words a form a machine could compute with. A word embedding maps each word to a vector, a point in space, so that words with similar meanings land near one another. The Word2Vec models showed that this space could be learned from raw text with no labels at all, unsupervised. One detail matters. The space is high-dimensional, several hundred coordinates per word. That room is what makes it work. In 2 or 3 dimensions, there is not enough space to keep every relationship apart. Any picture on a screen is a flattened projection of that geometry, and the learned space held a surprise. Simple vector arithmetic is meaningful. Take the vector for king, subtract man, add woman, and you land near queen. Add Germany and capital, and you land near Berlin. Plot countries and their capitals in this space, and the connecting segments run nearly parallel. One direction in the geometry means capital of. Distance encodes similarity, direction encodes relation. The headline: high-quality vectors trained on 1.6 billion words in under a day, on hardware of the time. Meaning had become geometry, and it was cheap. These word vectors are the ancestor of the embeddings that power modern retrieval systems, one representational level down, words rather than passages. But a limitation was built in. Each word gets one vector on its own, regardless of the sentence around it. Representing isolated words is not the same as handling language. Mapping a whole sentence to a whole sentence was the next problem. 2014. Sequence-to-sequence learning mapped an entire input sentence to an entire output sentence, trained end-to-end. One recurrent network, the encoder, reads the input word by word and compresses everything it has seen into a single fixed-length vector, sometimes called a thought vector. A second network, the decoder, unrolls the output sentence from that one vector, word by word. No hand-built linguistic machinery anywhere. The mapping is learned from millions of sentence pairs. On a standard English to French benchmark, this purely neural system scored competitively with the mature statistical translation systems of the day. A blue score of 34.8 against 33.3 for the strong phrase-based baseline. The first time learned end-to-end translation stood level with engineered pipelines at that scale. But look at the middle of the picture. Every sentence, short or long, squeezes through the same fixed-size vector. For long inputs, information is simply lost at the choke point. The bottleneck was not a detail, it was the architecture's defining weakness, and removing it was the next breakthrough. Attention came first as a patch to that bottleneck. Instead of forcing the whole sentence through one vector, let the decoder look back at every encoder state, at every step. Each output word computes a weighted sum over all of the input positions, and the weights themselves are learned jointly with the translation. This mechanism has a name you will meet everywhere: query, key, value. The current step issues a query. Every input position offers a key and a value. Matching the query against the keys produces the weights, and the output is the weighted blend of the values. Hold on to that triple. It returns in what follows. The weights form an alignment. For each word being produced, they show which input words the model is drawing on. Plotted as a grid, these alignments are strikingly interpretable. The model learns, on its own, which source words matter for each target word. The payoff shows up on long sentences. The bottleneck model's translation quality collapses past about 30 words. The attention model holds flat, even beyond the lengths it was trained on. The choke point was real, and attention removed it. One thing did not change. The network was still recurrent. It processed a sentence one position at a time, in order. Training remained serial, and serial meant slow, and slow put a ceiling on how large these models could grow. The radical step was still to come: keep the attention and throw away the recurrence. 2017. The paper was titled "Attention is All You Need," and the title was the thesis. The transformer discarded recurrence entirely and built the model out of attention alone. Every position in a sequence attends directly to every other position in both the input and the output. The architecture is a stack of identical blocks. In the encoder, each block is a self-attention layer followed by a small feed-forward network. The decoder adds masked self-attention so it cannot peek ahead, and an attention layer that reads the encoder's output. A final projection turns the top representation into a distribution over the next token. You do not need to hold every box in mind. The point is that the whole model is attention and feed-forward layers, nothing else. At its core, the same query, key, value pattern is compressed into one small formula. Compare the query against the keys and retrieve a weighted blend of the values, a soft, differentiable lookup. Why did this matter so much? Recurrence is serial, but attention is parallel. Every position can be computed at once, which is exactly what modern hardware is good at. Training much larger models on much more data became practical. The headline: New state-of-the-art on both standard translation benchmarks, trained in about 3.5 days on 8 GPUs, a fraction of the cost of the best prior systems. The honest cost, comparing every token with every other means, compute grows with the square of the length. That finite attention budget still shapes how practitioners fill a model's context window today. One more thing to name. Keep only the decoder stack, drop the encoder, and you have the architecture of the generative pre-trained transformer, the GPT line. Nearly every large language model in use today is a transformer. The transformer was an architecture. The next move was a recipe for using it. Rather than training a fresh model for every task, pre-train a single large transformer once on a huge corpus of unlabeled text, and then adapt it to each task with comparatively little further training. BERT did this with a simple self-supervised objective: hide about 15% of the words in a sentence and train the model to fill them back in, using context from both directions. No labels needed. The text is its own supervision. The representations this produces are contextual. The same word now gets a different vector in different sentences. Bank near river and bank near loan finally come apart. That is the step beyond the one vector per word geometry where this story began, and contextual embeddings of this family are what many modern retrieval systems actually run on. The headline: one pre-trained model with a thin task-specific layer on top set new state-of-the-art on 11 language tasks at once. Pre-train once, adapt cheaply became the dominant paradigm, and the family split into two branches. Encoder models like BERT specialize in understanding. Decoder models, the GPT line, specialize in generation. They are pre-trained to predict the next token, and they are the branch that leads to the models agents are built from. Everything so far happened by 2018. The stage was set for scale. Seen as a list, these are 5 loosely related papers. Seen as a chain, each one removed a specific limitation of the last. Word vectors gave meaning a computable form, but handled only isolated words. Sequence to sequence mapped whole sentences, but squeezed them through one vector. Attention removed that bottleneck, but kept slow, serial recurrence. The transformer removed the recurrence and made scale practical. And pre-training made a single model's knowledge transferable across tasks. This is a selected teaching lineage, not a claim that each advance was the sole cause of the next. Larger datasets, faster hardware, and other lines of work run alongside it. But the dependency is real. Each arrow in this chain is a limitation that the next step removed, and by 2018, the pieces of a general language substrate were in place. Here's the story on one card. These are 5 lines worth being able to place in an AI conversation. 2013, word-to-vec meaning as a learned vector geometry. 2014, sequence to sequence, whole sequences mapped end-to-end. 2015, attention, the decoder looks back at every input state. 2017, the transformer, attention replaces recurrence and scale becomes practical. 2018, pre-training, one model, many tasks, contextual representations. The key idea to carry away, meaning became geometry, attention replaced recurrence, and pre-training made one model transferable. What this part of the story leaves on the table is scale itself. What happens when the decoder branch grows 100 times larger and steering it by plain text becomes a working interface? That is a story of its own.